I'll introduce myself. I'm Brian Sather. I'm the Director of Product Marketing here at nTop. I'm here with Tristan Antonsen, who's our Technical Product Manager on our build team, and then Adam Lebrecht, who is an onboarding engineer. If you are a current nTop customer, you most likely know Adam. If you're not, hopefully you'll meet him soon in one of these onboarding sessions. So today, the topic of our webinar is all about accelerating advanced design for conceptual design of aircraft. We're going to give a quick overview of nTop. I'm going to do just a short presentation because I want to get into the live demo piece of this as quickly as possible, which Adam and Tristan are going to do. So I will just tee it up with a few slides and then we will transition over into the live demo. So here we go. First things first, a little bit about who we are. Many of you are probably familiar with nTop if you're an existing customer or you've been around us in the past. But just as a level set, nTop, what we do is we build computational design and analysis software. And the reason for that is we want to create highly flexible, real-time parametric models so that we can remove some of those traditional barriers to optimization and increase the speed with which we can iterate and move through our design process. Where most of our customers get the most value out of nTop are for things like highly engineered designs where it just benefits from more iteration or more design exploration. We are used on everything from concept through detailed design. Webinar today is going to focus primarily on concept design, but there are a lot of applications on the detailed design and optimization side of things that we'll cover in other webinars and other materials. And then just to quash any fears that you might have, we are not out to replace any CAD softwares or simulation softwares that you might use today. We're really meant to complement them, to enable a design exploration process, if you will, so that when you ultimately get to CAD, hopefully you only have to capture that idea once and you don't have to go through a bunch of iterations in your CAD software, which we know can be painful. So that's a little bit about us. In terms of what we're talking about today, we are, kind of focusing this talk or this webinar on development challenges on the concept side within aerospace and defense. And we're seeing a few key trends here. There was a report, it just came, I don't know if it just came out, I just saw it, where the Department of Defense commissioned a study on why is there such a significant increase in the cost of some of these major defense programs. And what they found was that things like material cost, wages, and things like that seem to be keeping pace with inflation and aren't necessarily the reasons why these programs are increasing more exponentially in cost. It's actually the complexity and the sophistication of the systems we're creating. So that's one challenge, right? Is things are getting more complex as we go forward. And at the same time, there's a lot more competition, both between companies, but also between countries. And it's resulting in these innovation cycles needing to shrink. What used to take something like 5 years, we now want to get done in about 18 months. And so we're trying to move much, much faster. Now, this creates what we these are things that come from customers in these industries, what they've framed as the lock-in trap, right? So we need to make pretty major decisions about our program and architectures early in the development process and with less insight than what we may have had before because we just aren't able to go through as many iterations of the design before we've got to go and select something and move forward. It locks in risks that we may not have seen. If those things get discovered late in the process and we've got to restart or go backwards, now all of a sudden the cost of that stuff goes really high, really fast. And those are the things that we hear about in the news. The second thing that happens is when we pick just a small sample of initial concepts to explore, we might refine those and optimize those initial concepts, but there might be regions of the design space that we could have explored a little bit further that would have been much, much better overall, even as a starting point. And it creates these missed opportunities. And so this is the core challenge that we're looking to solve is like, how do we drive more insight earlier in the development process so that we can identify those risks and really explore more of our design space and make good decisions early on about where these programs are heading. Now, the root cause of this, at least what we've can identify so far, is that it just takes too long to go from requirements to design, right? So we might start with initial idea, like we'd start with our requirements. We come up with an initial idea of what we think that could be look like, the solution to that could look like. We define our parameters of that model. We capture that idea in CAD. We move that model into simulation so we can understand how it performs against our requirements. And then we start making decisions, right? Is it good enough? Can we move forward? Do we need to start over? Is it so far off? Or do we think we can refine it and kind of move forward that way? But we need to make those based off of basically a single point of reference. Now, the second iteration and the following iterations is where it gets a little bit hairy, right? These things happen in serial in most cases. Now, you might pick two or three initial concepts to pursue, but each one is moving in a serial one by one process. Once we've identified the changes we want to make to the model or to the design, incorporating those changes into your CAD model is a very manual process, right? I was going through an example earlier this week where it was one loft of a fairly complex shape, but it's still one loft. It had two regions that were lofted together and then 25 rails on each side. It's all in 3D space, so you're dealing with three coordinates for each line. It's 150 parameters to modify one loft. It takes a long time to make these changes, and that's not very productive. It doesn't help us move fast. And then you run into the next issue is if we didn't build a robust enough parametric model in CAD, it just fails to update. Now we're going back through our model tree, trying to figure out what happened, where can we make it a little bit more flexible so that we can make the change that we want to make and ultimately get to that next step. Or worst case scenario, we're starting over and modeling the thing from scratch. And then finally, one of the challenges is that traditional simulation is expensive. Right? We're not talking about license costs necessarily or solver costs and things like that. We're talking about the time and investment you make in preparing models for analysis, doing the geometry repair, doing the mesh generation, doing the mesh repair, ultimately setting up the model in your CAE system. It's all hands-on keyboard, hands-on mouse time, and it just takes a while. And it extends the process even further. And so what we want to do is figure out like how do we make this a little bit more robust, a little bit more automated so that we can go through this in parallel and generate designs that kind of capture our entire design space. And it requires us to address these two key bottlenecks, right? If we summarize it, it comes down to these two things. The first is geometry, right? If you've made parametric updates in traditional CAD, you know it's fragile. And if you make anything that's too significant, beyond what you really set it up to do, it can require a lot of time, manual effort to either repair the model, update the model, or just start from scratch. And then the second thing is simulation. Like I said, preparing that data for analysis is an arduous task. Takes several people. A lot of folks have dedicated people who focus just on meshing. There's still all the geometry repair that may need to be handled, and it takes a while, right? Which makes high fidelity design exploration really, really difficult because that process, that loop, takes weeks every single time through. And then we can use low fidelity models, and they're fast to update, but they provide these low fidelity insights that don't necessarily increase our confidence or reduce our risk enough where we feel confident moving forward. And so what we want to try and look at is how do we accelerate this process, right? And the first thing we start with is same as what we do before. We gather the requirements, we translate those, start translating them into tech specs. But instead of coming up with a single idea, right? A single idea that we want to capture in CAD, what we do is we want to create a highly flexible parametric model that can be used to generate any potential variant within our design space. And that's what we're going to show today is how do we go through that process. And so in this example, we're changing wing sweep across multiple different angles. We've got models that can handle this really, really in a robust way. And that's the kind of the key is as we're building out these really flexible parametric models, they update every single time, right? We don't encounter, they're unbreakable, they don't fail in the way that CAD fails. And so that we can generate a wide variety of different designs. We can send them off to be simulated very, very quickly without some of the simulation errors that we have, or without some of the uh, geometry fidelity issues that we might encounter as we go through that process. And ultimately, what it allows us to do is explore more of our design space, right? If we can do that really quickly, and we can do that in an automated way, where up front we're saying, I want to evaluate this range of parameters, and I can automate the system and have it go through that, and it gives me these charts where I can understand how it's going to perform. I can explore that design space and really bring insight much further into the process. And that was one of the things a customer said to us, I think it was a couple months ago now, is I want an insights machine. And that's really what we're talking about trying to build, is something that allows you to get to the point where you know, when I change this parameter, this is what's going to happen really, really quickly. So that's what we're going to focus on today. Now, obviously, there's several steps in this process that we'll need to go through over time. We're going to focus on creating models, these highly flexible parametric models, and showing how that can be done across a couple different examples. In future webinars, we're going to dive into more of the analysis side of things, and then ultimately we will show some of the how do we explore more of the design space, whether that's through MDO or design of experiments and other approaches that we can use there. And so for this one, we're going to focus on building out the parametric model. And so with that said, I will go ahead and hand it off to Adam here to show exactly how that's done. So I'll stop sharing, Adam, if you want to pick it up.
Perfect. So yeah, we're going to go ahead and get started here, and I'll do a little bit of an overview of the general demo that we're going to do as well, and then Tristan's going to actually step in for our second half. So we're going to start off, and we're going to look at kind of our CCA file here, or our collaborative combat aircraft. And this entire file that we have, we can see is really properly sectioned over here on the left, where about each section is going to be devoted to each separate component. For my part of the demo here, we're specifically going to go through our wings file in our example, and we're going to specifically learn the techniques that we can actually use to create a single or a double paneled wing, and how easy we can adjust these parameters, as well as actually change the twist and dihedral of our wing as well. If we've never seen nTop before, I know we have some new people coming in today. Obviously, the 3D viewport at the center of our screen is where we're going to be viewing all of the output that we generate from the notebook here on the left. And in the notebook, we have a series of functions that will then calculate and distill all of this information in the viewport that we see in the center. So coming down to our wing blocks here, I'm going to go inside what we call a custom block in nTop, which is actually a series of functions that we've packaged inside one block. So basically, it creates a custom repeatable function for us to use in whatever way that we want in an above workflow. Specifically, this file here is dedicated to creating a single paneled or double paneled wing in this case. To go inside this custom block, I'm going to right click and open this custom block. And inside, I can see all of our sections that we have devoted to actually creating this wing that I'm going to talk through individually, and we can actually see it update on the screen in front of us. So you can obviously see in our input section here, these are going to be our necessary inputs for creating our type of wing, where we're going to start with our root point, which is going to be located at the front of our wing. We're going to dictate our root chord length, or the length of our chord across our center airfoil here, the wingspan that we're using across our wing, the quarter chord angle, and the taper ratio to help define what our relationships are going to be as we move along our actual wingspan, our NACA 4-digit code to actually distill what type of airfoil we're going to be using with this wing, and we also have our dihedral angle and the twist magnitude of our wing along the midline of our wing. With all of these inputs, we're then able to calculate each of the geometries in our sections below, going through our edges, then to our profiles, parameterizing these profiles to extend along the edges that we've created. And once we've created a volumetric version, we're going to actually mirror it and make our design symmetric, make actual planar versions of this wing, and then we can twist that wing along our planar profile and then give it our end dihedral. In our first section here, this is where we're going to distill our leading and trailing edges. These are done using some custom blocks that we've created as well that take in our root points as well as all of our above values, and they'll output lines that give us our leading and our trailing edges. In this case, this is a single paneled wing custom block that we've created. So the output that we get is just going to be a single line at the beginning and one at the back. And again, these were calculated using vector math under the hood, something that we are all familiar with, but hate calculating as well. So having this reusable block makes it a breeze to be able to create different wings. In a similar vein, we also have a two-paneled edge block that we have here today. And in this, we can then control our separate angles and ratios after we've crossed a panel ratio that I have located here as well. So in our final example down at the bottom, if I make this visible, I can actually see as I drag either one of these edge sets into my selected edges variable here, that we're going to have our final version actually instantaneously update. So when I drag in my single panel edges as my selected edge profile, I can see the rest of my actual workflow update here. And now I can see that all of these calculations have happened in those 2 or 3 seconds. And now we have a single panel version of this wing just from changing our edges that we've selected. If I wanted to change something like even my root chord length down to an 800mm version here, I can go ahead, hit this, and I can also see, again, the entire workflow run and be accustomed to that operation that I've just performed. Coming down to our next section then, we're really going to learn how we can take these edges that we've created and turn them into an actual usable 2D profile. So in our first case, we're going to have a selection of airfoils that we can choose from. These airfoils can be chosen either from a NACA 4-digit calculator that we've actually created inside of nTop to give us this actual distance field that we use here. Or we can also create a custom airfoil from any types of points or curves that we've brought in as well. So if you're looking to designate your own Bezier spline as a type of actual curve that you'd want to mirror or manipulate, you can create your own custom airfoil and use that throughout. I then have a block where I can select that. And then finally, I also have the ability to create a profile that mirrors whatever edges that I've chosen at the top. So we can see, even if I drag again my 2 panel edges into my selected edges input, I can see my profile alter, and we can kind of see what it's going to look like to actually sweep this airfoil profile over the lines of our wing. In our next section then, that's where we're going to do exactly that. So basically, we've taken our single profile that it will have a field that extends on forever in our Y direction here. And we have one that mirrors the same in our Z direction. But I really need to bring this airfoil in between our edges. And that's where we have our parameterization blocks. Basically, what I need to do in this case is take this old X field that we have located here. And I need to understand how we can actually have this X mirror the lines that we have along here. So these iso lines, we can see that they're perpendicular to the actual X field that we have, but we need to bend that X field to follow these lines. We can do these using some field calculations inside of nTop as well, which I think makes it a uniquely useful tool to be able to do something like this. So this is our old X parameter that we basically have here. But using our single panel wing parameterization block that we've created, if I view this field, I can see that we now have actually an X field that travels along the leading and trailing edges of our body in between. So I can see that when we create this final wing, it will follow the lines that we've created exactly. In a similar vein, we need to make sure that we're sizing the Z direction appropriately as we move along our wing as well. So we have the ability to actually change our Z or our thickness of the planar version of this wing as well. And if I view this adjusted field, I can see that as I move across our body here, that our Z or the height of our wing is going to variably change, and I can see decrease as we move along. So we're not going to end up with a really fat airfoil. We're actually going to have one that's proportional to the thickness of our body or how much we've actually swept that chord along our wing. To get a final version of our wing, we can combine this new X and this new Z using a remap field block inside of nTop, which is really a unique field to nTop that allows us to change our local coordinates of the actual body that we've used. So I can see rather than just this regular wing profile field that I've started with, excuse me, our airfoil profile, which will again extend on forever from where we've kind of entered with our profile here. I can actually change this so that it will sweep along the trailing or leading edge that I've created. Again, if I change any of our results from above, like our wingspan, back up to 10,000 or 1,000 even, we can see that this is reflected in the field that we've already created as well. So as we've gone along, we've correctly withheld this parametric relationship because again, nTop uses a visual programming interface with the notebook here rather than trying to maintain a pretty fragile CAD modeling tree like we might be familiar with. After our parameterization step, this is really where we're just going to trim this final field into a usable volumetric object. So from here, we can see when I remapped this field up above, if I bring this field up once again, that this continues after the one-sided lines that we've created. So what we're going to do in this step is I'm actually going to bring up this plane that we've created across our midplane, and I'm going to mirror these wings across. And when I view this field, I can then see that we've correctly done this operation, giving us a healthy distance field once again. And now if I create a volumetric version out of this, we have our first actual planar wings that we've created, where I just trim the field on either side. Now that we have a planar version, we can actually go ahead and start manipulating this by adding a dihedral or a mid-curve twist as well. We can get that mid-twist curve along our body here. And using our twist wing custom block, we can then twist this wing along to a designated degree at a designated location, again, using fields inside of nTop. So it might be a little bit difficult to see in this case, but we've actually done about a 20-degree twist. And if I actually drag this slider using the GPU modeling capabilities of nTop, we can actually see this twist update live. Now, if I let this go and do a more precise render, I can actually then see that 78, about 79-degree twist along our body. Our final step in this workflow then is going to be adding that final dihedral rotation to our wing. So if I take this twisted version that we've just created, I can actually do one more operation where I can do our dihedral angle. We have this set at about 5 degrees, but again, using the GPU modeling capabilities of nTop here, I can drag this same slider and we can actually see this wing operation flapping on our screen. So all of these calculations and blends are happening live on my machine, and we're able to actually see this output live on our screen as well. So really throughout this workflow, we can understand how we can really level up these traditional explicit components that we start with, such as points and edges. We can make these into 2D profiles inside of nTop, and then we can actually parameterize these across a wing to give us really unique volumetric operations extremely easily. And you can also see as I've changed all of these points, our workflow has been intact the entire time because of, again, the visual programming interface that we have here with nTop rather than that historical based modeling tree. I'm going to go ahead back up to our top workflow here, and I'll discard the changes I made. And I'm going to go ahead and pass the demo here on to Tristan, who's going to go over a little bit more about how we can integrate similar components to that single wing that we actually made to create the volumetric plane model that we see on the screen. I'll go ahead and stop sharing here, and I'm going to give it over to you, Tristan.
Alrighty. Awesome. Thanks, Adam. Let's share my screen now. Give it a sec. All right, you should be able to see nTop now. Okay, so what Adam just showed you was basically the way of working here where you set up a reusable function and then you reuse it a whole bunch of times everywhere else. So we've got the same file that Adam just had pulled up. This is the CCA style aircraft. And then, like I said, if you take the wings, take that principle, and then maybe think of some other things like ducting, fuselages, all of that, you end up with a bunch of building blocks. And then you can take those building blocks and then put them together to create something like this. So I'm going to walk through how this is made. I'm going to talk a little bit higher level than in Adam's demo, just again, because there's so much in here that the key thing to look for is how these different components fit together. So also show some basic principles, some building blocks, how they fit together, and then also how these types of features can be parameterized. To reiterate, this was made 100% in nTop. And there's a very good reason for this. It's not just because we want things to be in nTop. It's like what Brian was saying. The whole value here is being able to iterate extremely quickly and very robustly through a design space. So I put this model together. I have some parameters that I care about. I know that if I take those parameters, turn the knobs like within my specified bounds, that I'm going to get a meaningful result and that nothing bad is going to happen. So this is made with a combination of implicits and curves and then these other building blocks. So keep that in mind. I wanted to kind of reiterate this point about the curves as well, because if you've used nTop before or looked at our marketing stuff, we talk about implicit modeling all the time. And that is like the core of what makes nTop work the way it does and why it's so robust. But implicits aren't the only type of geometry, right? There are other things like curves that are absolutely critical for workflows like this, right? It turns out curves just are the best tool for the job when you need to do something like define a very precise profile, or like maybe the airfoil that Adam was showing you, right? That's a very specific equation, and you need to create a curve from that. But the good thing is that we have curves. They work in a very familiar way to people who have been using CAD, like really any CAD package, but especially NX, CATIA, Alias, that kind of thing. You can take those and then you can use those to generate implicits. So I'm going to kind of play with a couple of these parameters here just to demonstrate that. Where we have these curves here, you can see I have that kind of top profile, the bottom profile, side profile, but then everything else in between is implicit. So I can go in here, where is my parameter here, play with this one, and then you can see this middle part just kind of updates, right? And that's because the solid volumes here are all implicits. And then the curves are what are driving the really precise kind of bounds of those implicits. So I'm just going to play with a few other parameters here. We've got that angle there. You'll notice on the inside, I have a few different things. That's to illustrate, the design drivers that we want to package inside this aircraft. So as someone designing this, I don't know if this will come through in the compression of the video, but I can play with that and see kind of how it relates to the inside of my model. So we take that one, that's implicit. We can do other things. This is kind of a fan favorite, is the dihedral, like Adam was showing. So if I move that one upward, move it down, you can see this is like, if somebody has never seen implicits before, this kind of tends to freak them out because, right, if I zoom in here, we've got this blend and it's going over this hard edge. And then it's not like a visual trick or anything. This is real geometry. It's actually computing everything. And there's no risk of having a surface that isn't watertight. So we have those. The whole thing is parametric, as I mentioned before. So if I go up here, where's my interesting parameter section? You'll notice a few things. So I have some parameters like dihedral here, right? That is like the thing we care about is the angle of the wing there. There's some other stuff that we care about, which is like relative positions. So you'll notice these things like wing position. This is just a 0.45, right? What's that mean? Well, that's 45% of the way along the aircraft. And the reason that's important is because we don't just care about some number in space, like of how far the wings are from the tip. We care about the wings in relation to the rest of the plane. If you are using this in like an MDAO workflow, multidisciplinary analysis and multidisciplinary design analysis optimization, whatever that acronym is, you care about kind of parameter ranges here. So we would want to maybe iterate and take the wings from up here all the way to back here. Okay, so that's kind of overview of the model. Like I said, things to keep in mind are curves, implicits, and then building blocks. So we have this final geometry, but I also have the building blocks in here of the wings and the tails in there. The unique thing about working in this kind of procedural implicit way is, unlike with BREPs in CAD, where you're kind of like constructing one big set of surfaces, trimming things, discarding things, all of that, you have everything accessible to you along the way. So even though I'm kind of consuming these wings later to create the final body, I still have the wings as individual bodies elsewhere. So that's what you're seeing here. Okay, now I'm going to start talking through some of the actual features in here. So the first one I'm going to talk about is the fuselage. So if we hide all of this and then go down to the here, solid fuselage, we can see, here, let me hide the wings too. We can see this is one of the shapes that we care about. If I overlay it here, this is the area. So this is kind of the key way to think, right? Is like in pieces that you then you build and then assemble all at the end. So we have this, and then this is generated with curves like this one, like these. And these curves are parametric. This is actually a custom block as well, just like what Adam was showing. So if I open this, we can play with these curves. So in here, I have a parametric curve set up. And these are some parameters that somebody designing this might care about. So if I move that one, you'll see that'll pop over there. I've got things like the top height. So make that 300. Oh, that's the wrong one. Let's do the top aft top angle. So you'll see that change, or top angle, or maybe like windscreen angle, that changes. So we have this, and then we can just use this downstream in our other blocks. Okay, so we have that. The other principle to think about here is we have these curves. Well, how do we actually want to create the implicit body? One of the other big differences with implicit modeling is you work in CSG, so constructive solid geometry. This does exist in CAD. It's just sort of like done a little bit more behind the scenes, where you might sort of extrude something up to another surface. But ultimately, the goal is to combine shapes. So if we think about this fuselage then, well, what I did was I broke this down. I thought, okay, what are the simpler shapes within this that need to be made? So, well, it turns out, we can kind of break it up. Let me just think about the top of the fuselage, and then where's the bottom? The bottom of the fuselage. And we get this kind of funky looking shape. But that's okay. This is actually one of the strengths of implicits. You'll notice here, if I look at my field viewer, like this is actually an infinite shape. That's super useful, because what we know is we care about the top shape, we care about the bottom shape, and then we want to intersect them to blend them together. And that's never going to break. You can't really think this way in CAD because there's always that risk that things are going to break when you try to combine them, but that doesn't exist here. So it makes it so that you can kind of separate the problem into different components. So then when I take these, and then I'll make these transparent, you can see that my design kind of lives within that inner space. I've got a couple other bodies here as well, like the fuselage cowling there. But this is an important thing to make because people aren't really used to thinking this way, again, because of the fragility of CAD. I wanted to show another related example to this one, where it's the same principles in being applied to the duct that I'm about to show you in the model. So I have this duct here, right? And I have some shape over here, and then some other shape, and then I have a path in the center here. And I wanted to create this shape. Well, you can kind of think of it as, you can kind of think of this shape in a bunch of different ways. Maybe a swept trapezoid with fillets added. The way I thought about it was swept sides and then a swept top, and then you intersect those, and then you get this kind of round. And the reason for that is in implicit modeling, when you have something that's rounded or a fillet, you create that at the time when you combine shapes. And again, this is a little bit of a new way of working for a lot of people. But if I start playing with the parameters here, you can see this is a like kind of ridiculously powerful way of working, right? This will never break. Even if I go to some weird value like this, you can see the fillets don't break, they just disappear because they're not geometrically possible. Same here with the side angle, all of that, and that as well as the blend radius. So this blend radius here, I can go too far there, and again, it doesn't break, can make the whole thing disappear. Right? This is the fundamental principle behind a lot of this stuff. So if I go back over here and say, okay, we have our fuselage, and then now what we care about is the ducting, right? You can see that the same thing is being applied over here. Right? So I have these sort of infinite spaces, and I'm just saying the thing I care about is the intersection of all these spaces. Now, again, this might seem a little bit weird, but if you think about it, you can usually relate these things back to kind of design drivers. So in this example, I care about the fuselage, and then I want the fuselage to meet the top of the duct in a nice way, and then I want to then trim that later. And actually, this body is really useful because I can use this in CFD later, or I can use it to compute area ruling, all of that. So these end up giving you these sort of reusable tools for later on. So we've got that one, and then the wings and the tail, this is what Adam just showed you. So you know how this is built now. This is exactly the same custom block. Again, if you're not familiar with custom blocks, I have this here, and then I sent it via Slack to Adam earlier. Adam sent me some other custom blocks, like this landing gear custom block. Right, you can save them to your own library, share them, and then that means like this workflow is actually pretty fast to create because we had a lot of these starting points already. Right, I didn't have to start thinking, how am I going to make a wing? I just said, okay, let's put this wing block in here. Then the tails as well. The tails are created exactly the same way as the wings. They're just a slightly different custom block. In fact, Adam has a nice demo where he just takes a wing and then changes the dihedral, and then suddenly it's a tail, right? But in this case, I have this sort of mirrored tail custom block here. And then so now we actually have pretty much all the components that we need. So where's my duct volume? You think about combining all of these together, and then we will get our final design. So I'll go over that a little bit. I'm going to play with these blends a little bit more too, and then sort of show you what's going on here. So actually, this is a good opportunity to show off the new curvature visualization. So we have a couple curvature visualization modes. We've got a familiar zebra version, and then this metallic version. I'm going to keep it metallic because it looks cool, and then it helps us look at this blend over here. So this blend, I'm going to play with the parameters. Right, we've got the wing blend. You can see we've got that hard edge. It just works, right? People spend tons and tons of time trying to get stuff like this to work, and then you change a parameter, you have to completely resurface the design, and it's just a nightmare. But here, that's just not a problem. Like you kind of get these for free. I don't even really think about these anymore because it's just something that I know is going to work every time. The thing I did think a little bit more about is the size of the blend. So you might notice here, I changed to my adaptive resolution, then let that render. The blend goes from very large over here to very small over here. And this is where the field-driven design component of nTop really starts to come in. So if I look at my wing blend using our field viewer, you can see that blend size directly corresponds to this field, right? We have 100 millimeters over here. I mean, this is a small airplane, but 100 millimeters, 0 millimeters. And then that directly gets applied to the wing blend. And then also this wing blend, the field itself, that's not just like data that I imported. This is a field I generated parametrically in relation to all of the rest of the aircraft. So that same principle is applied over here. You can see it goes from large to small. And then that all comes together, and then we have our full complete aircraft. So just to end this part of the demo, I'm just going to play with a few more parameters. So we'll play with the chine angle again here. We've got the top radius, right? Go from pointy to rounded. And then if I go over here and make this transparent, I'm going to show all of my interesting curves and then internals. And then where it's my point here, if I drag this back, we'll be able to watch this whole thing update. So now you can see all the curves, all the landing gear, everything updated when I changed that parameter. We've got this. So if I toggle back and forth, you can see the visibility is also getting toggled there, but you can see that the whole thing updates. All right. So that was a lot, but hopefully it's kind of, inspires you to think about what you can do with nTop and the tools that are just in the software today. So I'm going to pass it back to Brian for some Q&A.
So if you have any further questions, please let us know and we will try and get to them. If you're interested in talking to someone on the team further about this, you can drop me a note or drop a note in the chat here before we wrap up, and we will make sure to get a hold of you after the webinar. But I just want to thank Tristan and Adam for putting together the demonstrations that you saw today. That was fantastic. Thank you everybody for joining the webinar today. We look forward to talking with you afterwards.